Welcome, everybody. Good morning, good afternoon, good evening. I'm very pleased to welcome all of you for this special webinar on mini-LED displays with our guests from Kulik and Sofa. So a few things to introduce the webinar. We're going to have several speakers. At the end, we're going to take a Q&A session. If we are not able to answer all the questions, we will get back to you within a few days to answer your questions. Just so you know, you are free to write your questions in the chat, and everything is going to be recorded on our end. Just so you know, also the webinar and the presentation in PDF is going to be made available on our website by tomorrow. Without further ado, let me start this webinar by introducing the speakers that we have today. My name is Inbo Hamri. I'm team lead analyst for the imaging and display activities within Yole Intelligence. We have Marc Lecomte, the innovation leader for optics within PZO. And we have Bob Shylock, the CTO and Senior VP of Central Engineering for Kulik and Sofa. During this webinar, we will have a talk coming from Yole Intelligence, one from Yole System Plus that I will give also, subbing because unfortunately one of our speakers is a bit sick. We wish him well for a prompt recovery. And then I will give the hand to Mark and then to Bob, and then we'll get to the Q&A session. So first of all, I wanted to introduce Yole Groups, just because, as you know, we've kind of rebranded ourselves a bit more than a year ago, and just wanted to let you know that the group is composed of Yole Intelligence, where we do technology and market research. You know us from that. We have Yole System Plus, formerly System Plus Consulting, very well known for technology, process analysis, teardown, reverse costing and engineering, and PZO, which is well known for characterization of electro-optical performances, risks, specifications, and so on and so forth. And you'll be able to see all the extent of what we're able to provide. We are a worldwide group based all over the world. The headquarters are in France, and I'm actually calling you from Tokyo. So we have a bunch of international speakers here because we have Bob calling us from the US, Mark from France, and myself from Asia. And Yole Intelligence, part of Yole Group, is composed of several different divisions, and I'm part of the Photonics and Sensing division, leading imaging and display. So without further ado, I will share the latest trends and market figures based on our latest reports that is available on our website. So first off, what's the nomenclature of LEDs? We know LEDs, we keep hearing about micro LEDs, and mini LEDs kind of came around, let's say 2018, and there was kind of a confusion for that. We try to nomenclature that in a sense that mini LEDs are up to, let's say, 50, 40 micron, and then down below it's micro LEDs. It's very important to make the differentiation because actually the applications are totally different. Here we are specifically talking about mini LEDs, and in mini LEDs you can either address backlight units for traditional displays like a TV or a tablet, and we'll see some examples, or for direct view LED displays, what you can see in, for example, when you go to Burger King or Costco or Times Square or whatever that can be. So here, really, the focus is going to be on mini LEDs and what applications they can bring. So in terms of context, so the addressable applications, as I said, are really oriented towards the traditional displays. So here you have a few examples: automotive, IT, VR, TVs, and you have also the tablets. And we know very much about the Apple iPad that was released with mini LEDs. Unfortunately, they decided to go towards OLED from 2024, which kind of killed the momentum for tablets. But we'll see that it's not really the end of the day for mini LEDs. Of course, as I was saying, we are talking about backlight units. So everything about smartwatches or augmented reality, extended reality glasses, or smartphones, it's not really, it doesn't really make much sense to talk about mini LEDs for that. So here are the applications on which we are focusing. there's a price competition between mini LEDs and OLED because at the end of the day, mini LEDs came in to supercharge what's happening in the high-end LCD TV market at the beginning. And the high-end market for TVs was really dominated by OLED, and there was kind of a gap that could be somehow circumvented by mini LEDs. Unfortunately, they kind of see this gap reducing because they are still expensive, and we will see that through the cost analysis performed by Yole System Plus. Here you have an example on how it can also be confusing either for the technologists or the consumers because same size, different technologies, but you see they're priced the same. Samsung TVs nowadays are mostly focusing in terms of high-end. They are mostly focusing on OLED with a QD OLED. And before that, it was mostly mini LED based. But they've noticed that it was a better path to go towards a QD OLED. And this is what is going to continue addressing the high-end segments. We can kind of anticipate that if the backlight unit cost can come down, and it will come down with efforts on the backlight unit in itself, meaning, for example, the number of LEDs you use, the size of the LEDs, the transfer that you use, the repair that you need to make. And that's why we have invited our good friends from Kulik and Sofa to give us more about what kind of solutions they can bring for mini LEDs. And so at the end of the day, they're probably going to trickle down. And the traditional quantum dot-based full area local dimming TV solutions are going to trickle down to lower than the mid-range. So much so that Korea kind of abandoned. I mean, here we are talking about the OEMs, and Korea is kind of slowing on what's happening in terms of mini LED for TVs, and it's mostly going to be driven by the Chinese OEMs. And as you're going to be able to see, we've torn down several of those, and lots of innovation and push has been provided by Chinese OEMs. One of the most adamant players was TCL, and now that Samsung is kind of abandoning that for the high-end segment, there's kind of a possibility for Chinese OEMs, especially being driven by their own internal market. That is why we anticipate that the growth for the two countries OEM are going to go that way. Everything is interested with Apple. And so here we kind of have a roadmap on what they're going to choose in terms of technologies for their future products. Here we are talking about IT products. So we anticipate that the MacBook Pro is going to be mini LED until OLED is being made available. And we're going to see in the next slide why we're talking about making it available. The thing is, nowadays, you need to, what's the word? We are seeing LCD fabs being closed. The LCD market is not that interesting anymore for high-end segments of OLED. And so we are, high-end segments of IT. And we are seeing OLED investments being made for IT products because this is where you can see the next potential of growth for display makers. Because as you know, the OLED smartphones shipments are growing, but not as such a fast pace as what we could anticipate for IT. That is why we've seen some several $1 billion investments from Samsung or BOE to try and reach the IT market. The thing is, if you make just a simple back of the envelope calculation, you can anticipate that just the depreciation costs that you're going to have on a panel are going to represent a few $100s, which means that OLED for IT is probably going to be, once it ramps up for very high-end equipment, high-end applications of IT. And so mini-LED will continue to exist maybe in more mid-range or niche products. Another opportunity for mini LEDs, we won't talk about it too much, but it's mostly what we are seeing in terms of automotive market. So there's a strong push since 2010 by LG Display and Samsung Display to try to get OLED into the OEM's cars. It took some time. They needed to develop a lot of the technology. Whereas nowadays we are seeing some design wins, there are some opportunities, they are shipping a lot, especially LG display. But there's a strong opportunity for mini LEDs because here the competition is mostly going to be around the cost. Whereas for backlight units, it's kind of a supercharged LCD, which is already qualified. So there's an interesting opportunities, and we are seeing more and more prototypes and press releases about automotive OEMs wanting to go the mini LED route for automotive. I went very fast because it was supposed to be a small introduction, but here, given everything that I've explained kind of quickly, this is how we are seeing the growth for the market until 28. So here we are talking about millions of panels. And as you can see with the small rocket, we anticipate that the biggest growth opportunity is going to come from automotive. And of course, IT is not to be neglected because even though there's a lot of push for OLED investments, we don't know that it will ramp up and be accessible to the mid-range consumers by 26 or 27. Hence all the opportunities. May have heard that mini LEDs are dead, but this is very, very, very far from it. Now, I'm going to transition and take the role of Sylvain Allereau from Yole System Plus. So once again, you know, Yole System Plus is very well known for doing teardowns, and we worked together also with PZO and our friends from the XOMark to open several kinds of displays to try and compare what was happening in terms of LED design choice, backplane design choice, driver design choice, assembly, optical films, and so on and so forth, and what it represented in terms of costs. So here we are going to compare two different mini LED TVs. One, which was the high-end from Samsung from 2021, and the latest of Skyworth. Why we're choosing those two? First, it's because I didn't want to choose the same as Mark, just to show you a bit more of what we're able to provide. And second, it's because the Samsung TV is a traditional passive addressing with a PCB, whereas the Skyworth was choosing active addressing on a GCB, so a glass board, which can bring lots of interesting opportunities for the future. So without further ado, this is usually what you can find in Yole System Plus reports. You're gonna have teardowns at several different levels. Here you are seeing what's happening in terms of dimming zones. And here I'm showing you the 5 different screens that have been chosen. So at first it was the iPad Pro, of course, first available for high volume. Then we chose the Samsung TV because it was the most high-end, most popular within the market. We also chose to go with the Samsung monitor to see if they were choosing different design styles depending on the applications, because the viewing angles are different, the viewing distance is different, and maybe the driving, the LED choice, and so on were different. Then we chose the TCL because TCL has been on the forefront of developing a new mini LED based technology, and you'll see a better example of that with what we call the 0D through Mark's presentation. And then the Skyworth TV, as I told you during the introduction, because it was a GCB with active matrix driving. So here I am going to show you different parts of the teardowns of just the two TVs I've mentioned. And then I will comment on the last slide, several things to need to keep in mind for these two TVs and how we can compare them. So here you can see that, for example, the Samsung die and the Skyworth die are kind of in a similar size. And if you look at the sizes, we are still talking about something that is quite big. When I say big, here we are talking several hundreds of microns. And as you'll see at the end for the cost analysis, the LED chip surface that you are using is directly correlated to the price of your backlight unit. That is why it is still expensive and not so highly competitive with OLED, especially with kind of the older white OLED that has fabs that have already been depreciated. Yeah, the pictures are at scale, of course. Here, it's kind of a summary in terms of numbers of what you have in terms of optical distance that we measured in-house, the number of LEDs per centimeter square, and so on and so forth. You can see there's quite the number of similarities overall. If you look, but however, if you look at the total number of LEDs, here we are talking about 50% more, bigger number of LEDs. You may say that it's because we are talking about 75-inch TV versus 65-inch, but that's not the only reason why that is so. We have a bit more zones, even though we have the same number of LEDs per zones, because how to say, it's a higher end product, the Skyworth TV versus the Samsung TV, in terms of MSRP. As you can see, the optical distance is quite different also, but we'll show you after that the kind of teardowns we did to explain why it is so. Here, in terms of optical distance difference, it's mostly related to the spacers that you are going to use and also the different optical layers that you are going to use to try and be as homogeneous as possible in your lighting pattern with your PCB or your GCB with mini LEDs. Again, there are many things to take into account here. I put just for information the kinds of color converting solutions that were used. So Apple went for phosphors, while Samsung obviously is using cadmium-free products, while TCL and Skyworth, as they were available mostly in China, are using cadmium-based solutions. I just put the TCL TV optical distance here, just as an illustration that it is the smallest. As I told you, it's a 0D solution as they marketed it. This is what we've found in terms of all the different filters. And Mark will tell you a bit more about what it represents in terms of optical measurements and optical performances and so on and so forth. So here, if we look at what it costs eventually, you can see that for the mini LED Skyworth, it's much more expensive. We can look at several different cost elements that are contributing to the structure. You can see that the drivers cost more than 50% more, because here we are using active driving, so you have to have many more drivers. In terms of mini LEDs, we are talking about quasi double the price, because as I told you, it's plus 50% in terms of numbers. Then there's a slight difference in related to the size, which was a little bit bigger. And then you have the assembly that is probably a bit easier when you are doing it on glass because it's more precise. And then to add a few more comments. So at the end of the day, Samsung has developed a polyvalent solution for the mini LED technology. They dissociated the digital parts and the current driver parts. So it's a very simple driving scheme, but it allowed to reduce the power consumption and to drive LEDs on a much larger area, hence the cheaper cost in terms of drivers. Their drivers that are using, let's say, two dies. You have one die that is the controller, and a very small current driver IC with only 4 channels that are assembled close to the mini LEDs. Just so you know, when we do the teardowns, we also have all the information about the drivers because we cut them off. We look at the nodes, the number of metal layers, the size that they represent, and so on and so forth. But here, for lack of time, I had to skip this illustration. So Skyworth, they went to active matrix. Why? Let's think about, it's not about the technology, it's about the application. And here was to enhance the picture quality and reduce the image flickering. Then the space is kind of 50% thicker on the skywards, as you've seen previously. They have a thicker spacer. It's probably to obtain a good light uniformity because they're using many more LEDs. As for the kind of driver they're using, it's kind of standard, but as it's active, you need to use many more drivers. So you have one per LED. At the end of the day, it's a very simple basic driver that is less than 0.2 millimeters square in terms of surface. And then to conclude, think about how the glass circuit board technology is kind of 10 times more accurate than a standard PCB technology when you want to do assembly and then repair. So you could imagine that at the end of the day, it could be possible to assemble smaller mini LEDs because this is the single bigger contributor to the cost. The thing is, it hasn't been done for this TV, but we may see what happened in the future. So that concludes the part on there. So I'm gonna give the screen sharing to Mark. I thank you for your time, and I will let Mark now take over.
Okay, thank you, Zine. Oh, I don't have the access of to share my screen.
Should be on the bottom.
Yes, but no, I don't have the. Oh, okay, this one.
It's okay, don't worry.
Okay.
We are used to Zoom bugs and whatnot. It reminds us of bad times we had a few years ago.
Okay, that's me. Little moment. Okay, so I'm going to show you the analysis of we carry out on the Samsung TV Neo Q LED and the TCL TV Pro 85 inches. So on the left part, this is the Samsung TV, which use all-in-one plate for the optical film stack, and on the right the TCL TV, which uses the OD0 technology, OD for optical distance. That means that the first surface of the optical films is in contact with the mini LEDs. Some words about the architecture on the Samsung Neo QLED. The optical plate is positioned at 3 millimeters from the LEDs, thanks to the spacer attached to the PCB. And the optical plate itself is composed of 8 optical films, and in the middle of the optical stack, there is a 0.7 millimeter thick layer of glass, which is used to reinforce the plate and to serve as a substrate for the other films. The function of the films of the optical plate is to homogenize the light, the blue light from the mini LED, to convert the blue light into white light, and to reinforce the brightness towards the viewer. On the TCL TV, the optical film stack is also composed of 8 layers. The first of them is in contact with the PCB, the mini LEDs. This first layer is a relatively thick diffuser to homogenize the blue light from the mini LEDs. And also it reinforces the backlight unit. The first 4 layers of the optical stack are only stack, and the last 4 layers are bonded together to the LCD. And the function of the optical stack is the same as for the Samsung TV. So it homogenizes the light, it converts the blue light into white light, and enhance the brightness towards the viewer. Some words about the mini LEDs. Samsung uses mini LEDs different from TCL, and Samsung use mini LEDs with 2 dBr for distributed bright reflectors, one at the top and a second at the bottom of the mini LEDs chip. In this configuration, the blue light is mainly extracted from the side of the mini LEDs. TCL uses mini LEDs with only 1 dBr mirror placed at the bottom of the mini LEDs chip, and in this configuration, the light is mainly emitted along the normal of the PCB.
Mark,
Yes.
I'm sorry to cut you off. There was an issue coming from the chat. Apparently, the slides were not changing. So actually, this is Hélène moving the slides for you, because there was an issue with your sharing. So could you please start again, maybe slightly quicker from slide 24, and mention every time when you need a slide change, please?
Okay.
So yes, we are back to slide 24, and please mention to Hélène when to change the slides. Thank you. Sorry for the chat.
So this is the about the architecture of the backlight units. On the Samsung TV, the optical plate is positioned at 3 mm from the mini LED. And thanks to the spacer attached to the PCB, the optical plate itself is composed of 8 layers attached together, and 0.7 millimeter thick layer of glass is used to reinforce the plate. And the other layers convert the blue light from the mini LEDs into white light, homogenize the light, and enhance the brightness of the backlight unit towards the observer. Next slide, please. On the TCL TV, the optical film stack is also made up of 8 layers. The first, starting from the PCB, is in contact with the mini LEDs. This is a relatively thick diffuser to homogenize the blue light from the mini LEDs, and also to reinforce the backlight unit. In this optical stack, the first 4 layers are only stacked, while the last 4 layers are bonded to the LCD. Their function is to homogenize the light, to convert the blue light into white light, and to reinforce the brightness of the backlight unit towards the viewer. Next slide, please. So some words about the mini LEDs. The mini LEDs used by Samsung are different than those used by TCL. Samsung use mini LEDs with two distributed bright reflectors, DBRs, one at the top and the second at the bottom of the mini LEDs chip. And in this configuration, light is mainly extracted from the side of the mini LED. TCL, on the other side, TCL uses mini LEDs with a single DBR at the bottom. And in this configuration, the light is emitted mainly along the normal of the PCB. Next slide, please. So we carry out some photometric, goniophotometric measurement on the mini LEDs alone and on the wall display, the wall backlight unit, excuse me. So on the Samsung TV, you have to see the graph on the bottom right part of the slide. The goniophotometric measurement of the mini LED confirms that the blue light is emitted mainly from the side. And in that configuration, it is possible to illuminate a large part of the optical plate with few LEDs over a short optical distance. Here we have 3 millimeter for the optical distance. And after the optical plate, the measurement shows that so this is the graph at the top right part of the slide. We can see that the light is redirected towards the viewer in an angle of 110 degrees. Next slide, please. Thanks. On the TCL TV, the measurement of the mini LEDs alone shows that the light emission is quasi-Lambertian in an angle of 120 degrees. And we analyze that the homogenization of light takes place mainly into the first layer of the optical stack. And this first layer is a 2.4 millimeter thick diffusion plate. After the optical plate, after the optical stack, excuse me, we can see, so the graph at the top right of the slide, we can see that the light is redirected towards the viewer in a narrow angle of just 40 degrees. Next slide, please. So after the backlight unit analysis, we then analyze the brightness behavior of the entire screen as a function of angle. So we measure that the loss of brightness with the horizontal angle is better managed on Samsung TV than on TCL TV. The half brightness angle on Samsung TV is 45.5 degrees, while it is just 31.6 degrees on the TCL TV. And we can note that there is a correlation between the brightness angle of the backlight unit and the brightness angle of the display. And in our case, the Samsung TV has both the highest brightness angle of the backlight unit and the highest brightness angle of the screen. Next slide, please. So in summary, the TCL TV has a thinner backlight unit thickness and the higher backlight unit brightness and higher peak screen brightness. On the other hand, the Samsung TV has a better backlight unit and screen luminance uniformity, as well as a wider brightness angle. And the last slide, please. So this is the same result, but as above, but presented under the graph you can see. So that's all for me. Thank you for your attention.
Thank you, Mark. Thank you, Mark. So now it's my pleasure to introduce Bob Kayak, who will explain to us, as the CTO and Senior Vice President, Central Engineering, what can they bring to enhance the mini-LED display industry. Please, thank you. The floor is yours.
Thank you. Hi, I'm Bob. I'm going to talk a little bit about KNS, just to present who we are, and then get into our LED transfer technology. So KNS has been around for a long time, since 1951. We have over 3,000 employees globally, and we're headquartered in both Singapore and Fort Washington, Pennsylvania, which is near Philadelphia. Our revenue in 2022 was over $1.5 billion. We make equipment for semiconductor manufacturing, so we're sort of famous for our wire bonders, ball bonders, and wedge bonders. We have a whole range of advanced packaging machines, flip chip machines, thermocompression bonders, lithography, and SMT combined with flip chip, dispensing, wafer level bonders, SMT, as I mentioned. And one of our growth vectors is advanced display. So we came out with a machine called the PixelLux. It does 50 die per second, and we've shipped hundreds of them for backlighting application. And we've just recently developed the Luminex, which is the successor to the PixelLux. The PixelLux uses mechanical die transfer, and the Luminex uses laser for die transfer. And that's what I'll be talking about today. So for advanced display, as I said, we have the Luminex. Major benefits is it's configurable for all applications: sorting, mixing, repitching, die bonding, or mass transfer. It has two different modes of operation. One we call position correction mode, 100 hertz at 10 micron 3 sigma, or a multi-pattern placement where we can go substantially faster depending on the dicing quality. And I'll discuss that later. And we have a scan mode that can go up to placing a 10,000 die per second. So let's talk about the mini-LED process. So as you create a mini-LED, you have the epitaxy, the dicing, and then in most cases, die sorting and mixing. There's possible repitching or die bonding to the final substrate. So the Luminex can be applied to the sorting, mixing, repitching, and die bonding applications. So let's talk about the Luminex. So we call our technology LEAP, which is laser-enabled advanced placement. The way it works is the LEAP process uses a laser, which interacts with a special tape called a dynamic release layer. When the laser fires to the DRL, it forms gases, and the gases form a bubble or a blister. So this rapid expansion of gases causes the surface of the material to act as a micro machine, and it propels the dye off the tape across a small gap onto a substrate. There's different laser transfer processes. However, this process is, our process is patented, so it doesn't contact, and it's the only laser transfer process where the reaction byproducts can be isolated and contained so the dye are not contaminated. So there's no debris, there's a containment layer, and that's the Canis patent. So the dye are mounted to a glass carrier with a special tape called DRL, as I mentioned. The special laser fires for picoseconds, creates the blister that I mentioned, and the blister ejects the dye in microseconds. The blister is contained, and a high-speed galvo moves and directs the beam to the next dye and fires again, and so on. The dyes can be transferred to solder paste, flux, ACP, or another tape. So you can see, you know, in the graphics how that works. In this case, the gap is 150 microns. On this slide, we show an LED with a high-speed video camera. So this video camera is capable of 700,000 frames per second. You can see that the dye is ejected on frame 558, and it ends up on the substrate on 560. So that's about 10 microseconds, and the dye is traveling, in this case, at an average velocity of 25 meters per second. This is the dye firing without a tape, a substrate underneath it. So you can see how the dye looks as it's being fired across the gap. For the laser-based transfer architecture, we move the dye on the glass substrate over the final substrate, move the substrate very close to the dye which are going to be transferred, and then the dye are transferred within a 50 millimeter by 50 millimeter field of view. And then, of course, then we move the dye around the substrate and fire to different fields of view until the target substrate's populated with dye. So again, the dye are mounted on the DRL with the pin side facing the substrate. They're placed onto flux or solder. It's a special solder. And then they undergo normal reflow and light up. We also have from our dispensing division, we can create conductive adhesive onto the final substrate very quickly at something like 20,000 dots per second. So in production, we're targeting 99.999% yield, and we've reached greater than 99.99% yield with 100% light up. So the different modes of operation, we can transfer one dye at a time, and we can get to 100 to 150 hertz with transferring one dye at a time, compared to pick and place, which is 10 to 20 hertz. We can improve the productivity by transferring more than one dye at a time. So if the die are aligned above the substrate in an increment of die, we routinely transfer 4 die at a time. And depending on the dicing accuracy, we can go to more die simultaneously. So this is higher productivity, 400, 600, 800 die per second if this can be employed. So we call this multi-pattern placement. And this is an example of 400 hertz with the 2x2 MPP mode, multi-pattern placement mode, where we create an application at this productivity. And then mass transfer is if the die are perfectly diced, meaning they're etched or plasma diced, we can transfer die up to 10,000 hertz. So this is really suitable for RGB of small die and micro LEDs. So maybe a board of RGB die might have 250,000 die. So in this case, it would take 25 seconds to populate all colors. And generally, one machine would be set up for red, another for green and blue in a inline system. Another benefit of LED transfer compared to maybe stamping transfer is that there's selectability. So in this graphic, you can transfer all the good die and skip the bad die or die of a different bin. You can refill them later. There's also rework capability where we can heat up a bad die that maybe doesn't light up and individually transfer another die to replace it for final bonding. So the commonly pick and place is used for backlighting mini LED, and that's a bit slower process. And as the die gets smaller and smaller, pick and place has die size limitations, while laser transfer can be extended below maybe 0406 size die, where pick and place kind of reaches it's difficult to pick these small die. So if you take a 10 or 20 hertz pick and place application, you can populate backlighting in anywhere from 8 to 16 minutes, possibly marginally acceptable. And an RGB of 256,000 die would take hours. Whereas with the laser, we can do backlighting in 12 to 66 seconds and a full RGB in 8.5 to 28 minutes. And we're looking at possible improvements in that productivity also. So we have a solution for mini LED. We want a solution also for micro LED. So the transfer gap plays a big role in the accuracy that the machine is able to attain. The Luminex has superior accuracy for this micro LED because of the nature of the micro LED. So for a mini LED, the minimum fly distance is a function of a safety zone that maybe should be around 100 microns. If the die lands on its side or tombstones, as the wafers moved, it could cause issues. But once the sapphire is removed for a micro LED, that safety distance can be decreased quite significantly. So the flight distance is lower. And as we can see from this graph, as the transfer gap gets lower, the 3 sigma accuracy gets better. So for, a mini LED flying across maybe 150 to 180 micron gap, we can get to about a 10 micron accuracy at 3 sigma. And for a micro LED, which flies only across a smaller gap, we can get close to 2 micron accuracy. And of course, we have to control that gap very well. So we have confocal sensors and piezo stages to real-time tilt the substrate stage, so we can maintain a gap of about plus or minus 5 microns. So there's also interspacing for micro LED or small. And you can see from the graph on the left how many million of micro LED dye per 6-inch wafer can get onto that wafer as a function of the interspace. So for a kind of a larger micro LED, it's not super important. But as the LED size gets smaller and smaller, the amount of dye that you can get on a wafer varies tremendously as a function of the gap between dye. So here I have a precision of dye that are spaced 2 microns apart, which is the minimum gap that we've seen from customers. And the accuracy shows that there's a process window of amounts of energy that yield 100% that can get down under 4 microns at 3 sigma with gaps that small without affecting the neighbor dye. Here's just some examples of dye at various gaps that we've worked with. And we've done studies at different gaps, and with at least with this 40 by 20 micron dye, the precision is down around 2 micron for all gaps. The spot size, so we actually don't put one spot on the LED. We break the laser up into multiple spots with the DOE, the dichroic optical element, and we can actually get spots down to 2 or 3 micron. So we've been developing this films with our partners, and we've studied iteratively what happens with different films, and we're engineering the films to get accuracies. Our target would be 2 micron. So this is an example of micro LED transfer. So here's the dye before transfer, and here's the dye after transfer at 1,100 hertz for a 40 by 20 dye. So in summary, the Luminex is a fully developed platform with laser transfer technology. It's a successor to the Pixelux. It can do sorting, mixing, repitching, dye bonding applications for both backlighting and RGB for mini LEDs. We're running mini LEDs at yields of better than 99.99%. Our target is 5 nines. We're extending this technology by working with several customers and material suppliers in developing a micro LED process. Better than 5 micron accuracy and 99% yields are achieved today with different materials and different process flows. The flexibility of the Luminex allows it to be applied to different processes for different products, So it's one platform for multiple tasks, not only what you need today, but also what you need tomorrow. So, so that concludes my presentation. Thank you.
Thank you very much, Bob. Still have a few minutes, so let's take this opportunity to go for a short Q&A like this. So yeah, Rob, don't move too far because actually the first question is for you.
Okay.
So must the GaN always be on sapphire for the laser transfer, or can it be on a silicon substrate?
Yeah, it can be on a silicon substrate. We've actually considering applying this technology to ICs. So things like RFIDs and small die applications, this technology can be applied to, and we've demonstrated that transferring die to flexible circuits, silicon substrates, and PC boards. So we can transfer into both flux or paste if necessary.
I see. Thank you. We have a question for PVO. Mark, could you tell us what is the benefits of using an all-in-one plate, please?
Well, the main benefit to use all-in-one plate is lies in the manufacture of the screen. It is faster to assemble the backlight unit parts with fewer potential errors in the position and orientation of each layer. And the all-in-one plate combines all the backlight units' optomechanical functions. So it's a simpler way to manufacture the backlight unit of a screen.
Okay, thank you, Mark. I have another question for Bob. So when we look at the images that you provided, it looks like the dicing was very, very, very nice. How does this dicing affect your productivity at the end of the day?
So if dicing is done with a blade and the wafer is stretched, the distance between die varies. So the machine will not be able to transfer a lot of die simultaneously. It will need to maybe we can only transfer 4 die at a time. And if the die are diced almost perfectly, maybe with a plasma dicing, then the laser can be positioned on many die simultaneously, and the productivity can go, from 150 hertz up to somewhere 400, 600, maybe even 1,000 hertz by transferring 4, 6, 8, or 10 die at a time. And so the dicing distance is the better it's controlled, the higher the productivity we can achieve.
I see. Thank you. Thank you very much. And still another question for you. I'm sorry. You are the star of the show. So you talk a lot about your DRL. Do we need different DRL tapes for different applications or not?
Yeah. For miniLED, we have 2 suppliers that have a tape that are optimized, and those tapes work for a range of die sizes. For micro-LED, the tape there again is also 2 suppliers, and we have a different DRL for micro-LED. We also have UV DRLs, which are very sticky. So when you transfer the dye onto the tape, it's sticky. Then we irradiate the tape, and it becomes much less sticky, and it's compatible with the laser transfer. It's easier to get off the dye off of the tape when it's less sticky. So yeah, there are different DRLs, but generally for one application type, there's one type from multiple suppliers.
I see. I understand. Thank you very much. Due to a lack of time, we won't be able to take any more questions. I've seen a few of them in the chat. As I said, we will get back to you shortly with answers. I thank you for your time. Just to conclude, I just wanted to highlight the fact that everything that we've shown is based on several different reports that we did. So we have our technology and market report focused on backlight units and not TVLDs that was released this summer from Yole Intelligence and from Yole System Plus and from PZO. We have two types of reports. We have several different specific types, one per display among the 5 that I've shown, with many more details than what we could illustrate. And we have one that serves as kind of a executive summary in which you won't have all the details, but maybe some of the major information that you would be looking for. This will conclude this webcast. So I want to thank all of you for staying until the end, asking questions. And I want to thank once again Bob from Kulik and Sofa to have been around and give a presentation with us. As I said at the beginning, the replay and the presentations will be available tomorrow, or at worst case by next Monday. I wish you a good day, good afternoon, good evening, or a good night. As for myself, it's going to be good night. Thank you all, and take care.
You.
Bye.
Bye.
Bye-bye.